led to the explosive growth of the web. In the same way that HTTP connected disparate hosted web pages, ACP, or Agent Communication Protocol, uses HTTP to connect the diverse ecosystem of standalone agents. It provides a way for agents to communicate and collaborate with one another easily, no matter what framework they're built on or technologies they leverage. Building complex multi-agent systems, like agents performing search, writing, editing, or tackling workflows, requires collaboration with other agents to accomplish a shared goal. There are many frameworks that target this agent development, but the ability to plug and play with agents from different frameworks is an unmet need. Today, most agents lack a shared protocol for communicating with one another. Connecting agents built using different technologies requires developers to build brittle and non-repeatable integrations, which are also susceptible to the constant changes pushed in the frameworks. ACP provides a unified interface for agents to communicate, regardless of their framework. One of the key values that ACP holds is open governance and community collaboration. This means instead of just being open source where developers can look at the code and request changes, but decision-making is made by a single or group of companies, ACP's open governance invites the community to shape the roadmap. So ACP becomes a protocol shaped by the community for the community, much like HTTP. ACP benefits not just the developer, who doesn't need to constantly rewrite integration logic, but also the end user, who will receive better results because there is more choice for the developer to choose the best agent for the task. Now you're going to learn some of the exciting patterns that ACP makes possible. First, dynamic updating. With how fast innovation is advancing in this field, the agent that was best last month is often not what works best this month. And as we just discussed, making an agent ACP compatible means that you can swap agents in your systems, even if the new agent was built using a different technology. This makes your system truly interoperable and can be very useful for testing what agents give you the best performance in your system. Specialized agents can work as a team. So instead of building one giant agent to handle everything, ACP allows teams of specialized agents to collaborate dynamically. If you had a research agent collaborating with an agent that creates a beautiful visualization and an agent that is especially configured for financial modeling, then when you ask for a report, the agents could hand off tasks to one another, just as teams do when they collaborate. You can also create across-company workflows. Companies rely on many platforms like a customer relationship management platform, enterprise resource planning, human resources systems, project management tools, and many more. For example, if a retail company uses a customer support platform and an ERP system to manage their inventory and logistics, each system could have a dedicated agent to manage tasks. So if a customer submits a complaint about a delayed shipment, the customer support agent can recognize that it needs the assistance of an inventory agent and sends a request using ACP. Each agent stays focused on its domain, but collaborates using ACP. Now, ACP also opens up the opportunity for inter-organizational collaboration. You'll build out an example of agents communicating from different organizations with Nick. But in a nutshell, ACP can enable agents from different companies to securely collaborate, even when they're hosted by completely separate companies. This opens up a whole new world of possibilities, as we move from just using agents internally to making our agents available to external providers so companies can work together. ACP also supports human-in-the-loop collaboration so that you can ensure that your agentic system is operating responsibly and to your expectation. In the next lesson, we'll learn more about the architectural componentation layer, and what's sometimes called the operational layer. It uses HTTP and the REST architectural style to facilitate communication between independent systems. ACP is based on a client-server architecture that uses a simple REST interface. This means that the client is responsible for initiating communication, and the server responds to that request. In ACP, both the client and the server can be an AI agent, a human, or a microservice. The client will always initiate the request, and the server will always respond to the request. In a basic example of an ACP interaction, where the server host is an AI agent, the ACP client discovers available servers and then initiates a request. It sends a REST request to the ACP server. The server, which wraps an AI agent, manages the request and returns a response back to the client over REST. As things get a little bit more complex, we can observe how multiple layers of protocols, each serving different purposes, can work together. In this diagram, we see a client makes a request to an ACP server over REST, which wraps an agent. The agent determines it needs to invoke a tool, so it sends a request to an available MCP server to execute the tool call and return the result. Once the ACP agent completes its run, it returns the output to the ACP client. Before you dive into building out your first ACP-compliant agent in the next lesson, let's go through some core concepts that will help you understand how the protocol works on a deeper level. Agent detail is where you define your agent's basic identity and capabilities. You can specify the agent name, provide a description, and add optional metadata for additional information. This basic information makes your agent discoverable and usable within the ACP ecosystem. The agent detail enables both online and offline discovery. Online discovery occurs when ACP servers are already running and can be accessed through their API endpoints. Offline discovery happens at a higher level, like at the agent catalog or registry, where agent detail is embedded in the agent package, allowing a user or system to discover agents without requiring them to be running first. This enables the creation of an agent catalog or directories where agents can be browsed, selected, and then spawned when needed. To activate your agent and enable its online discovery, you need to deploy it. You can either use the SDK built-in server, which is the easier way to get started, or use an external server. Starting the ACP server makes the agent available to the ACP client to run. The built-in server is what you'll be using throughout this course. Once the agent is activated, it's ready for execution, meaning it can actively process requests and generate a response. ACP offers 3 execution modes: synchronous, asynchronous, and streaming. In synchronous mode, the client waits until the agent completes its run and then returns a final result. In asynchronous mode, the client doesn't wait for the agent to respond. It can carry on with other tasks in the background. When streaming, the server establishes an SSE, or server-sent event connection, which provides real-time updates as the agent generates results. Regardless of the execution mode, each run progresses through states such as in progress, awaiting, and eventually reaches a termination state, such as completed or failed. The agent communication protocol is designed with a production-grade environment in mind, so it prioritizes security, scalability, and observability for reliable performance at scale. One frequent question is, what is the difference between using ACP, MCP, or A2A? And put simply, MCP is designed for enriching a single model's context with tools, resources, and prompts. But MCP and ACP are compatible and even complementary. An agent might use MCP when making a tool call that returns more context to the agent, and then that agent might decide that it needs to communicate with another agent, which it does over ACP. However, MCP is decoupled from ACP because it's not primarily designed for agent-to-agent communication. For instance, as of now, the MCP protocol is not designed to easily enable an agent to carry over a task from another agent, or peer-to-peer collaboration. When it comes to shared memory, MCP has the support for session management, meaning servers can be stateful and maintain information about a client's sessions between requests. However, MCP doesn't handle the state itself. The ACP SDK supports centralized storage for runs and sessions, meaning that multiple ACP servers can persist information across these runs or sessions. For message structure, MCP doesn't form any opinion on the message. Since agents need to support natural language as well as other modalities, ACP messages follow multimodal structures for exchanging content. Google's A2A protocol, which was introduced shortly after ACP, also aims to standardize communication between agents. Both protocols share the same goal of enabling multi-agent systems, but they diverge in philosophy and governance. Some of the notable differences are that both A2A and ACP are open source, but ACP is openly governed with the Linux Foundation, ensuring it's open, neutral, and centered around community participation. In ACP, you can run multiple agents with the same server, reducing overall setup and management effort, whereas with A2A, each agent must be run with a separate server. ACP also follows the REST-based architecture style, supporting standard web infrastructure and patterns that enhance scalability and interoperability. A2A uses JSON RPC style, which can introduce a bit more complexity. In A2A, the agent output and message history are separated. This can make it very difficult to determine the order of events in a multi-agent turn without implementing additional ways of persisting this information, which is really important for transparency and observability. ACP supports a wide range of agent types and allows developers to explicitly choose between synchronous, asynchronous, and streaming modes. This makes response handling predictable and simplifies client logic that guarantees streaming via SSE. A2A also supports both stateless and stateful agents, but the interaction mode is determined dynamically by the agent. As a result, clients must be built to be flexible in handling sync, async, or streamed responses based on the agent capabilities. While ACP and A2A have some differences, it's important to highlight that they have a lot in common. What you learn in this course with ACP should largely carry over to A2A. You now have a handle on when you might use ACP, MCP, or A2A based on your goals and system configuration. It's important to remember that these protocols are all living and breathing projects that change rapidly, and what might be true when filming this course could easily be out of date in the near future. So always make sure to do your own research and confirm any assumptions with your own experimentation.
This is pretty straightforward, but we're going to take it step by step nonetheless. So first up, what we need to do is bring in a couple of dependencies. So we're from Crew AI, we are going to import a crew, and this forms the basis for the architecture of a multi-agent system. We're going to have a single agent, but we kick things off using the crew itself. We're then going to be able to define a task, and this is where we're going to pass through our prompt as well as our desired output. So effectively, our task contains everything that we actually want to do. We're also going to bring in an agent, and this is going to be our LLM plus our tools, and that brings us to our LLM. We're going to bring that in as well. So we've got our LLM provider to be able to create an agent. Now, the nice thing about building a retrieval augmented generation system is that a number of providers have made it a lot easier to go and chunk up and vectorize your data. So we are going to do exactly that. The nice thing about Crew AI is that it comes with a RAG tool. So let's bring that in. So we're going to, from Crew AI tools, we are going to import the RAG tool. So this RAG tool is going to facilitate us building up a RAG system. So if I go and run that, that is now all run successfully. Now, there are a couple of warnings when you go on ahead and run this, so we're just going to ignore them for the time being. And to do that, we are going to import warnings, and we are going to filter warnings and ignore those. This means that we're not going to get any unnecessary warnings that we don't necessarily need. The next thing that we're going to need is an LLM, right? So retrieval augmented generation is all about having a vector database and querying that vector database, bringing back the context, passing it through to our LLM, and generating the output. To generate that output, we're going to need an LLM. So let's go on ahead and bring that in. So I'm going to define a new variable called LLM, and that is going to be equal to our LLM class that we brought in from Crew AI. So to define that, I'm going to create a new LLM, and we're going to specify the model. I'm going to set that to OpenAI GPT-4, but you could use a range of other providers. You could use Olama, you could use watsonx, you could use a ton of other providers. This is just the one that we're going to be using for this example. So if you want, plug in a different one, see what actually happens. So the next thing that you're going to need to do is define how many maximum tokens you want to allow our LLM to generate. So to do that, we're going to specify max tokens and set that to 1024. So if you'd like your LLM to be able to generate more or agent to be able to generate more, you could bump that up. Likewise, if you want to be a little bit more conservative with how many tokens you're generating as part of your agent system, you might choose to bump that down. Okay, so that is our LLM now created. Now to build up our RAG tool, we first up need to define a bit of config. So let's go ahead and do this. So I'm going to create a new dictionary called config, and this is going to contain our LLM as well as the embedding model that we want to go and use. And this specific config is all for our RAG tool that we imported from Crew AI. So we need to define what LLM we're going to use to generate output, and we need to define what embedding model we're going to use to embed our chunks as well. So let's go on ahead and define this. So we're going to define a new key called LLM, and within that dictionary, we are going to have two values, provider and config. Our provider is going to be equal to OpenAI in keeping with the theme, and the specific model that we're going to be using is going to be contained within the config key. And we're going to set that equal to model, and you guessed it, GPT-4. Now, we've talked about our LLM, but we really need an embedding model as well. This is what is going to take the chunks from our document and convert them into a method that we can search inside of our vector database. So we are going to create a new key called embedding model, and then we're going to specify another provider. And again, we're going to set it to OpenAI. And then we need our config. So we're going to specify config, and this time we're going to specify the embedding model that we want to use here. So we're going to set that equal to model, and then the value that we set to model is going to be text embedding ADA 002. So this is the config that you're going to use for your RAG tool over here. But again, feel free to update this if you need to. So I'm going to run this. That's our config now defined. Now, so far we've gone and set up our config. We've set up our base LLM. We need to go and define our RAG tool now. So again, Crew AI's got our RAG tool that you're able to use to be able to go and define this and build up your agent system. So we're going to create a new variable called RAG tool, and we're going to set it equal to RAG tool, or an instance of RAG tool. And then to that, we're going to pass through three different values. So we're going to pass through the config, and we're going to pass through the config dictionary that we just defined up here. We're also going to specify the chunk size, and we're going to set that into chunks of 1200 tokens. So this means that we're going to be chunking up our document into chunks of 1200. And we probably want a little bit of overlap just to make sure that we're not cutting off chunks in the incorrect places or places which aren't so ideal. Now, that's our RAG tool sort of defined, but we also need to add a document to that. So how do we actually go about doing that? Well, I've got a document over here, and this is going to be stored inside of the same environment that you're running, so you'll be able to access this. This is a PDF document about potential insurance inclusions. Now, this agent that we're going to be defining is going to be all to do with finding out what's included, potential waiting periods on insurance. So we need to provide a document which contains that specific information. So it's almost like a product disclosure statement for an insurance policy. Now, we want to get this into our RAG tool. So how do we go about doing that? So the first thing that you're going to go on ahead and do is define this RAG tool, obviously, but the next thing that you want to go on ahead and do is actually add that document to the vector database. So we are going to go and use the add method from our RAG tool and specifically add in that document. This is going to be contained inside of the environment that you're working in. But again, if you want to do this locally, you'd go and update this path to the document that you want to embed and load into your vector database, aka your RAG tool. So to the add method, we're going to pass through the file path for our document. This is currently stored inside of the root folder and then inside of data. And then we are going to define the specific name of the file, which is gold, hospital, and premium extras.pdf. So if you've got a different file name, you would go and update the file name for the document that you're working with right over here. We also need to define the data type. So we're going to specify the data type, and we're going to set that equal to PDF file over there. So if we go and run this, this should start chunking up our document and push it into our vector database. And that looks like it's run successfully. So we've gone and defined our LLM, you've gone and defined your config, you've got a RAG tool. Now, when are we going to define the agent? Well, it just so happens we're going to do that now. So in order for you to define your agent, we're first up going to define a variable, which is going to contain the agent. And then you need to go and use the agent class, which we had right up there. So we're going to define a new agent, and this is going to contain a few things. But this is kind of why I like Crew AI, because it's very verbose in how you go and build one of these agents. The first thing that we need to define inside of our agent is the role. And this is the role that that agent is going to take. Now, keep in mind, we're going and loading a product disclosure statement for an insurance policy. So we are going to have a senior insurance coverage assistant here. So that's going to be the role for our agent. Now, we also need to define the goal. So we're going to specify our goal as determine whether or not something is covered or not. And this is all to do with whether or not something is covered within your insurance. It might also talk about waiting periods, so on and so forth. Really, it's all to do with the information contained within that PDF. And then we want to go on ahead and define a backstory. This is probably my favorite key. And so the backstory in this particular case is going to be, you are an expert insurance agent designed to assist with coverage queries. So you can see that we've now gone and defined our backstory. Now, we also need to define a few more things. So you're going to go and set verbose equal to true. This means that as our agent is running, we're able to see active progress. You're going to set allow delegation to false. This means that we're not going to be passing off the task to other agents. You're also going to pass through your LLM over here. So this is the LLM that we defined up there. It's the OpenAI GPT-4 instance. But we also need to pass through our RAG tools, because so far we've gone and defined it, but we haven't actually given it to our agent over here. So under tools, we're going to create a new list, and we are going to pass through our RAG tool that we've now gone and defined. And the last thing that we need to define in order to create our agent is the maximum retry limit. So we're going to define that and set that equal to 5. This basically states that our agent's going to try to get the answer at least 5 times, and if it doesn't, then it's going to error out. So this means that it's, again, a bit of an insurance policy that you don't go and blow out your number of API calls. So if we go and run that, that looks like our agent has now successfully run, and or not necessarily run, but we've now gone and defined it. The next thing that we need to do is define a task, and this is going to contain our prompt. So inside of our prompt, or our prompt is going to be encapsulated inside of our task that we've got over here. So let's create a new task. So we're going to create a variable called task1, and this is going to be an instance of the task class from Crew AI. Now, task has a couple of key things inside of it: a description, the expected output, and the agent that we want to delegate this particular task to or give it to. So the description, the first prompt that we're going to be passing through is, what is the waiting period for rehabilitation? Now, again, you might go and try a different prompt there. You might choose to try something which you see in this document. If you go and use a different document, this is where you'd go and pass through your specific prompt. We then want to define the expected output. So inside of your expected output, we are going to set that as a comprehensive response to the user's question. You might choose to change this a little bit. It might be a summary, it might be bullet points. You're effectively describing the style here. Now, remember, the last thing that you need to define inside of your task is the agent that you want to give this prompt to. So we're going to define that right over here. So we're going to specify the agent as the insurance agent. Remember, we defined the insurance agent over there. It's now coming into our task down here. Now, if we go and run this task, that cell has now completed successfully. So we've now defined our agent. We've now defined our task. We now need to encapsulate it all inside of a crew and then kick it off. So how do we do that? Well, remember, when we went and imported our dependencies, we imported a crew. So we're going to define a new instance of our crew. And we are going to pass through a few key things here. We need to pass through the agents themselves, the tasks. If we had multiple tasks, we'd pass through multiple tasks. We also want to specify that it's going to be verbose. So inside of our crew, we're going to define our agents, and this is going to be a list. And right now, we've only got one agent. But if you had multiple agents, you'd pass multiple through. But now, we're just going to have one single agent over here. We're then also going to have the tasks that we want our agent to complete. For now, we're just going to have task 1. If we had multiple tasks, we'd pass them in through here as well. And we're going to set verbose equal to true. That way, again, we get output progress as our agent is running. Then all that's really left to do is kick off our task. So to do that, we are going to create a new variable called task output. and we are going to take our crew from over here and run the kickoff method. This is akin to like running the crew or actually starting things, or when you hit enter in ChatGPT or hit enter inside of an LLM system like Olama. So that should get everything up and running. The last thing that we want to do is print out our final task output. So if we go and run this, this should hopefully kick off your RAG agent and get your agent running. So if we go and run it, take a look, you can see crew execution has started. We've gone and passed through the prompt to our agent. You can see that we've got our chunks from our RAG system. If we scroll a little further down, take a look, we've got our final answer displaying over here. So the waiting period for rehabilitation coverage under this insurance policy is 2 months. However, if the requirement for rehabilitation is due to a pre-existing condition, the waiting period extends to 12 months. It's important to consider this information can vary on the specifics of the situation, so on and so forth. You get the idea. The answer is now here. So again, we've got a bit of metadata, and you can see this is the output from actually printing through the actual task output from over there. So if we wanted to go and push this to a different system, if we wanted to output to a JSON document or something of the sort, we've got the ability to work with that final output as well. But again, keep in mind, you can go and change this prompt. So you might choose to change this query over here. You might choose to change your insurance agent, or even change the data that you pass through to your RAG agent. But for now, we've gone and defined our initial RAG agent. So over here, I've got the existing code that we wrote in lesson 3. This is the exact same insurance RAG agent that we've already built out. But how do we convert this into an ACP compliant agent, and specifically an ACP server? Well, first up, what we're going to need to do is run this as a standalone server. So we need all of this code to be output into a file that we can run using Python or UV. So how do we go about doing that? Well, we would typically use an IDE, but for this specific learning environment, we're going to use a magic function that will copy the contents of this cell into a Python script. And we're going to export this into a file called crew_agent_server.py. So when we go and run this cell, it's actually going to export all of this code to that specific file there. Now, the next thing that we're going to need is a couple of dependencies to actually convert this into an ACP server. So we're going to bring in the ACP generator from collections.abc. This is going to form the output type for the server. We're also going to import message and message part from the ACP SDK. This is going to form the format that we use to output the results of our agent. While we're at it, we're also going to import run yield resume, and server from the ACP SDK.server class. Run yield and run yield resume are going to form part of the asynchronous generator. So this effectively showcases the type of output that our ACP server is going to be exporting. The server itself is going to form the foundation of our ACP server. Okay, so those are the main dependencies now import. Now, the next thing that we need to do is create an ACP server. So to do that, we can create a new variable called server and assign it to our ACP server that we've imported from over there. Then what we're going to need to do is begin wrapping our existing agent. So I'm going to scroll on down to where we had our agent, and we're going to use the server.agent decorator. This is going to tell the ACP SDK that what comes under here is an agent that we want to make available on the ACP server. Now, the name of the agent that actually goes into the server is based on what we actually named this function, and we're also able to provide metadata via the docstring. So let's go on ahead and start wrapping this. We're going to make this an asynchronous function, and we're going to call it policy agent. Then we need to define what types of input we're going to take, and this is effectively where our prompt is going to be captured. The first variable that we're going to capture is our input, and this is going to be a list of messages. Then we're going to return a generator. That means we're able to iteratively return output from our ACP server. And that is going to be an asynchronous generator, and that's going to take in run yield and run yield resume from over here. Now, one of the most critical things is also explaining what these agents are useful for. So ACP makes this available through the docstring. So all we need to do is provide a docstring underneath our function. So our policy agent, if you remember correctly, is specifically our insurance-related agent. It provides us with information around our coverage periods, whether or not something is included or not. Now, we're able to provide this back to our users via the ACP server using this specific doc string here. So we're going to write it out. So this is an agent for questions around policy coverage. It uses a RAG pattern to find answers based on policy documentation. You can use it to help answer questions on coverage and waiting periods. So that's pretty much our doc string now defined. Now, when somebody looks for metadata around this agent via the ACP server, they'll be able to return that particular bit of information. Now, we need to tab all of this in, and there's one key thing that we need to change here. Right now, we've got a fixed prompt, which is being passed through inside of our task. But we really want to be able to capture a dynamic prompt when a user goes and calls out to our ACP server. And this is where our input variable from up here comes into play. Now, we do need to unpack the values from that input, because right now we're saying that we're going to be passing through a list. But for now, we just want to take that one prompt. So to do that, I'm going to convert this static prompt to an input variable. So we're going to grab the first value from our input, and we're going to grab the first part, and we're going to specifically return the content. Now, if you actually go and print this out, you'll actually see that when we return that message variable, we're able to actually extract all of those different components. So if you had multiple prompts, you've got the ability to maybe loop through and create multiple tasks. Maybe you try that out after this. Okay, so that is our task now amended. Now, because we are running this asynchronously, we want to kick off our agent asynchronously as well. So we're actually going to await our crew.kickoff method, and we're going to convert that to asynchronous. Now, right now, we're not actually returning anything from the server, so we need to return something as well. Now, rather than returning, because we are producing a generator, we're actually going to yield. So we're going to use the yield method, and we're specifically going to return a message, and we're going to return the different message parts from our agent. Now, this is going to take in our task output. Now, let's say you had another agent and it just returned back a specific text prompt. You'd be passing through the text prompt inside of this value here. Keep in mind, we're formatting it as a string. That way, we're keeping consistent when it comes to generating our outputs. But when we go and run this now, after our agent gets kicked off, it'll take in the prompt from our user over here. We're then going to unpack it and push it into our Crew AI task. And then eventually, we're going to return it down here. Now, we do need to run this server, because keep in mind, we're going to be outputting this as the crew_agent_server.py file. So how do we go about running this? Well, we're going to use a pretty common Python structure. So if name is equal to main, then what we're going to do is we're actually going to run this server, and we're going to run it on a specific port, because a little bit later on, you're going to spin up another server so we can build sequential ACP server calls. So we are going to take our server, and we're going to use the run method to kick it off, and we're going to run it on port 8001. Now, if I go and run this cell, this is going to output it into that specific folder. So my_ACP_project, and we're going to output it to the crew_agent_server.py file. So if you go and open up that file, and specifically inside of that repository, you'll see that we've exported this code that we've just written over here. Now that we've got that code exported, though, we can actually begin to run that ACP server. So to do that, we're actually going to create an iframe inside of our Jupyter Notebook. That way you can start up the server as well and give it a go. So I'm going to grab this code, which will open terminal 1. Now, we're eventually going to run multiple ACP servers. So we're going to run this server in terminal 1, and then later on, we're going to define a hospital server, and that's going to be running in terminal 2. Now, if we go and run this, we should get our terminal back and take a look. That's our terminal. And right now, you can see that we're inside of the work folder and inside of the My ACP project folder. Cast your mind back, when we went and wrote this out, we were writing out our crew agent server file to the My ACP project file. Now, if you're going to run this locally on your own machine, just keep in mind that you need to be in the same folder where the crew agent server is currently running. So we're going to be using UV to run this. Now, if you've never used UV before, you can install it by just running pip install UV. And if you're creating this for the first time, again, on your local machine, you're going to need to initialize a new project by running UV init, and then creating a virtual environment by running UV venv. We've already set this up inside of your environment, so you've got the ability to just go and kick off the Crew AI server. So to do that, we can run UV run crew agent server.py. And if we run this, hopefully we'll get an endpoint back that shows us that our server is running. And take a look, we've got our endpoint return. So we can now see that our server is currently running at our local host environment on port 8001. Now remember, we specified our port up here. Now, the thing about this is that it's going to stay up for 120 minutes. So if we start this server this first time, it'll run for 120 minutes. But if you go away and come back to this lesson, you're going to need to start it up again. This only applies to this environment. If you're running it locally, it's obviously going to stay up for as long as you're running the Python script. But just keep in mind that when you're running it inside of the deep learning.ai environment, you got 120 minutes. So now we've got the ability to call out to it via an ACP client in the next lesson. We've come to the time actually making a call out to our ACP server. Well, first up, we probably want to double check that our server is still running. So we're going to run through the exact same method that we did to get our server up and running. We're going to open up the terminal, and then what we're going to do is we're going to render terminal 1 exactly as we did previously. So that way we can just double check to see whether or not our server is up and running. Because remember, if you're running this inside of the deep learning.ai environment, it's going to stay up for 120 minutes. If you're doing it locally, it runs for as long as you've got the server up and running or the Python script running. So if we go and run this, we can take a look to see what's happening with our server. And take a look, it looks like our server's still up and running. You can see it right over there. Now, what we want to do is begin making calls to our ACP server. And the nice thing about this is that you can have a standardized client, or eventually you're going to be able to integrate it into different systems using a similar style pattern. For now, what we're going to do is we're going to make sure that we can nest async IO calls or async IO calls. So we're going to import nest async IO and apply that to our environment. This allows us to run the ACP client from the Jupyter Notebook environment. And then what we're going to do is we're going to begin building up our client. Now, within the ACP SDK, you've got a client available. And think of this like a way to just communicate with our ACP endpoint. We're also going to bring in async IO to be able to make asynchronous calls. And we're also going to import Colorama and specifically the for library. This just makes it so that you can output stuff using colored terminal formatting. It just looks a little bit nicer. You're able to see things a little bit more clearly. Then what we're going to do is we're going to create an asynchronous function. So we're going to create a function called example, and that's going to return nothing. And then we're going to connect to our client, and our client is going to point to the URL where our ACP server is running. So right now we're going to set our base URL and set it equal to localhost 8001, because if we scroll on up, you can see that it's running there. Later on, if you've got different servers running, and when we begin making sequential calls, we'll have to connect to 2 different clients because we're connecting to different servers. And even though we've only put 1 agent on this particular server, you could have multiple. And I'm going to show you how you might call that to different agents on a single server. So we're going to define that as a client. And then what we're going to do is we are going to run a synchronous call to that particular server. And we're going to target the agent that we defined. Because remember, the agent that we defined was our policy agent. The name of the function when you define the ACP server is going to be the name of the agent when it comes to calling it with the client. And I'll show you what I mean in a second. So we're going to create a variable called run, and this is going to await a synchronous call. And then we're going to target our policy agent. Remember, when we defined our agent in the ACP server, we named the function. So we typed in DEF policy agent. So policy agent was the name of the function. That then becomes the name of the agent when we use ACP. There's one last thing that we need to pass through to our client in order to run a prompt or trigger a prompt. And the cool thing is that when you go and run this, you'll actually see the call kick off in our ACP server up here. So inside of the input argument, we're able to pass through our prompt. So I'm going to pass through what is the waiting period for rehabilitation. Remember, we've asked this previously, but we had it hard-coded inside of our agent. So all things holding equal, this input should then be passed through to our agent running on the ACP server. So we should be able to see that pass through and run up there. Now, we're also going to print it out back into our Jupyter Notebook, so that way we can see it a little bit more easily. And to do that, we're going to print and we're going to use the Colorama yellow color, and then we're going to unpack the output from our client. So we're going to get the first value from our output. We're going to grab the first part. This is a similar way to how we actually unpack our input prompt when we went in to find our server. And then we're going to grab the content. And then we're also going to reset the terminal coloring using Colorama over there. So this should really just be our client now done. Now, if you wanted to, you could go and change the prompt here to something different. Try running a different prompt, see how the ACP server performs. Remember, it's going to be limited to what we've actually put inside of our vector database. But you might try uploading different documents and try different inputs, different prompts as well. And eventually, we're going to link these up to make sequential calls to multiple servers and connect multiple agents together. Okay, so if we run that cell, that looks like we don't have any issues there. And then we're going to use async IO and the .run method, and then run our function over here, which is called example. So if we go and run this now, as soon as we trigger this, we'll be able to see whether or not it's running up here in our ACP server. So if I go and run this now, take a look. Execution has started. You can see that we've got our prompt pass through. What is the waiting period for rehabilitation? Looks like it's all running. We're getting all of our context and our prompts. And all things holding equal, we should get a completion. Take a look. The waiting period for rehabilitation in the insurance policy is 2 months. We should get this printed out here as well. So take a look. We've now made a call to our ACP server using the ACP client.